Welcome back, everybody. We really only have 3 weeks of lecture left, which is really surprising here. So we're really getting close to the end. Just a reminder about the activities for this week. We're going to be going today and Thursday, we're going to be talking about a new section, L'Hôpital's Rule. It's a section that probably should have been introduced a while ago, and I'll explain a little more of that later. But so we'll have lecture today and Thursday, and then on Wednesday is our test over Chapter 7. And we did a review on that on Thursday. You've got the review problems there. For the most part, that exam is going to be integrals, as you would probably expect. So one of my big recommendations is that you study how to start each of these integrals. How do you make a decision about where to begin? And you're going to want to have that list of 6 things in your brain. So you can go down it and eliminate, well, I can't do this and I can't do this, so this is the only thing that I can really do. That's really going to help you on this exam. I'm hoping you're going to be able to see the board here. I've got, where I normally do lecture is otherwise preoccupied, so hopefully this is not too small. I'll try to write big as well. The section that we're going to go over today is the last section that we're going to do in Chapter 7. Working pen here. So this is section 7.7 called L'Hôpital's Rule. Okay, this is not pronounced L'Hospital's Rule. So please don't say L'Hospital. It's L'Hôpital. It's actually French. It's also sometimes spelled this way. Okay, and I'll give you a little bit of history behind this rule. But let me talk a little bit about the rule first before I give you a little bit of history. This rule is related to limits. Which harkens us back to Chapter 1, I think. And but it also involves derivatives, so we obviously couldn't have gotten to it at least until Chapter 3. Most calculus books put L'Hôpital's Rule in with what you would see in Chapter 3, and I think for the most part, I wish this book had as well. It didn't. There's a reason it's introducing it at the end of Chapter 7. There's further sections in Chapter 7 that we're not going to get to. We just don't have time. But this is a rule that I think is critical for you to see. One of the things that at least is nice in introducing it at the end of the class is that your final exam is going to be over some of the main topics from this whole year. And I am going to have a few limits on there. So this is going to be a good review of limits. It'll remind you of some of the things that we've done previously. I will review some of that stuff, but just so you're aware, so you remember, hey, you can't just take those limits and throw them out of your brain. You do need to remember some of what we went over. And the other thing about this tool we're going to see later is that this tool actually allows us to do some limits. It allows some of the limits that we did previously. We can do them much faster. The other thing that it lets us do is it lets us do some problems that we were never able to do before. And that's always the really nice thing about math tools. We develop a new tool. It either helps us do what we could do before faster or easier, or it lets us do problems that we could never do before, or both of them. In this case, it's both of them. So it's a really nice tool. So just to review some of our limit techniques. Okay, this is we had a list of things when we first went over limits. We had a list of things that we normally, when we approach the limit, we would say, here, do this first. If that doesn't work, do this. If that doesn't work, do this. So that's what I want to review here. So the first thing that we always try was to plug in. Do you remember that? Just try taking the limit. In other words, try letting the limit go to that number and see what happens in the function. So if I have a limit as x goes to 2, just try putting 2 in and see what happens. That doesn't always work. but in many cases that's a great starting point to figure out what's happening. Okay. Next thing that we had is if we're looking at a fraction and the top and bottom both go to 0, then we had some different things that we would try in this case. Do you remember this? So one of them that we would try was we would factor the top and bottom and cancel. Okay, we'd factor and cancel, like if you had x squared plus minus 4 on the top and x minus 2 on the bottom, you'd factor the top and then try to cancel an x minus 2. Another thing is that if we had a square root in the top or the bottom, then we would use what we called the conjugate, right? So if you had the square root of x plus 2 on the top, then we would multiply the top and bottom by square root of x minus 2. And that would help get rid of some nice cancellation would happen. It made our lives a little easier there. So that was another one. Another one that we had is if we had fractions in fractions, then we get a common denominator or otherwise simplify the fraction. Remember that? We have fractions in fractions. Then I kind of wrote down, well, if all else fails, just try to figure out a way to simplify things. And then we had, if you were looking at an absolute value, then we would come from both sides. You remember a problem like limit as x goes to 2 of absolute value of x minus 2 over x minus 2. Do you remember a problem like this? So then we would have to look at coming to 2 from the left side and coming to 2 from the right side. Another example that we had, take a seat here just for a second, is that if we had a fraction where the top does not go to 0 and the bottom goes to 0, then something else happens here. This is actually an infinite limit. And then we have to look at, just like up here, we have to look at both sides and figure out, is it positive or is it negative? If the top and bottom are both positive, then it's blowing up to positive infinity. If the top and bottom are both negative, then if the top is positive and the bottom's negative, for example, then we're looking at negative infinity. Okay, is that familiar? Does that sound reasonable? Another one that we had was this showed up later when we're looking at infinite limits. When we're looking at a polynomial or over a polynomial. So, for example, if we're looking at the limit as x goes to infinity of x squared plus 4 over x squared minus 3x plus 2, problem like this. Do you remember how we solved that kind of problem? We would, if it's a polynomial over a polynomial, we divide the top and bottom by the highest power of x on the bottom. Remember that? So we divide the top and bottom by the highest power of x on the bottom. Okay. So that was another technique that we had. And finally, we had one last one, which was the squeeze theorem. Remember this? So this was for examples like limit as x goes to 0 of x squared times the sine of 1 over x. So x squared goes to 0, but this thing oscillates. Remember, sine 1 over x did this going into 0. So we would squeeze this function. Sine sits between -1 and 1, and then we'd multiply everything through by x squared. That would let us squeeze everything down to 0. Okay. Hopefully these things are sounding fairly familiar. There are some problems that we couldn't do before. Even with all of these techniques, we still couldn't do those problems before, and we'll see a few examples like that when we get to L'Hopital's rule. Okay, but this is just a review of the limit techniques that we had previously. All right. Let me just give you two examples of ones that none of these limit techniques will actually allow us to do. So if I look at, for example, limit as x goes to infinity of x over e to the x. The top here, when x goes to infinity, x obviously goes to infinity. E to the x, when x goes to infinity, e to the x also goes to infinity. So this seems to fall, if I plug in, that doesn't work. This doesn't work, this doesn't work. This seems to work, but it's not a polynomial over polynomial, so this technique that I had before actually doesn't work for us. So I don't have a technique yet that allows me to do that problem. Another example similar would be the limit as x goes to 0 from the right of natural log of x over 1 over x. Both of these, this thing goes to negative infinity, this thing goes to positive infinity, but again, these techniques don't apply. So we need something that's going to help us, that's going to make things better. So let's give a little bit of history of the rule that I'm about to give you. This is actually a really cool rule. It works really nicely. So first of all, the history. The rule that I'm about to show you is named after the Marquis de L'Hopital. So the Marquis de L'Hopital. But the Marquis de L'Hopital actually was not the one who invented the rule. The rule was invented by Jean Bernoulli. And the Bernoulli family, it's actually a very famous mathematical family. There were a ton of mathematicians, like 3 or 4 generations of mathematicians in this family. The Bernoullis were very famous for developing a number of different things. But what happened back then, if you wanted to study mathematics and you didn't have a university position, or even sometimes when you had a university position, in order to focus on mathematics, you needed somebody to support you, to sponsor you, to give you some money, so that you didn't have to work, you could focus on just your mathematics. It's very similar to what happened for composers at the time, like Mozart or Bach. Mozart and Bach oftentimes had what were called patrons. They were people who had a lot of money who would support them so that they could do their work undisturbed, so they didn't have to have another job. And it was not uncommon at the time in composition for someone like Mozart to compose a piece, and then the person who paid him for his time got to put their name on that piece. So, like, for instance, if I had a lot of money and I hired Mozart and I said, okay, I'm going to give you a year's stipend just so you can write music, but I want you to write one piece that I can put my name on. Then Mozart would write one piece, and then that piece would come out published. It would say, Robert Myers wrote this piece. I didn't actually write the piece. I just paid for Mozart to be able to write it. The same thing happened here with L'Hopital's rule. The Marquis de L'Hopital was actually the patron for Jean Bernoulli. But Bernoulli actually developed the rule, and later the Marquis de L'Hopital actually paid for it, and so therefore wanted to put his name on that rule instead. So if you want to call this Bernoulli's rule instead of L'Hopital's rule because you're angry that L'Hopital got the credit for it, you're welcome to do that. You can call it Bernoulli's rule instead of calling it L'Hopital's rule. L'Hopital's rule only applies to what we call indeterminate forms. Okay, indeterminate forms. It's been a little while since we've done limits, so I'm not sure if you remember what an indeterminate form is, we talked a little bit about this when we did limits before. But an indeterminate form is a form where when you try plugging in and you get this form, you can't immediately tell what's going on. So let me give you a couple examples here. So 0 over 0 is known as an indeterminate form. And the reason is that if you have a limit, let's say I have a limit as x goes to a of f of x over g of x, and the top's going to 0 and the bottom is going to 0. So in other words, you have 0 over 0. You cannot tell what that limit is going to be. Let me give you a couple examples. So it could be, for example, the limit as x goes to 0 of 2x over x. So the top here is going to 0. The bottom's going to 0. What's the overall limit for that, for this function, if I were to cancel? Limit would be 2, right? And you can see if I, instead of putting 2, I put 5, the limit could be 5. So if I have 0 over 0, please never, ever, 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 I'm going to get your attention here, please never cancel these zeros and say that the limit is 1. Never do that. Ever, ever. Okay? I used to have professors who would be like, if they ever saw 0 over 0 equals 1, they would just put a big red slash through the entire paper and you get 0 on the entire thing. It was just like anathema to them. Okay, so please don't ever do that. 0 over 0 is an indeterminate form. You cannot tell what's going on. Okay? In a similar way, infinity over infinity is also an indeterminate form. You can't tell what's going on there. So let me give you an example there. So if I had the limit as x goes to infinity, let's take the same example that we did before, of 2x over x. Well, the top here is going to infinity, and the bottom's going to infinity. But you can see if I cancel the x's, this limit ends up being 2. And again, I could change the 2. I could put a 5 there or a 10 there. So infinity over infinity, you cannot tell what that is. Do not cancel those infinities and say it equals 1. Does not. Okay? Similarly, if the top is infinite, so if I have infinity and the bottom's infinite, and it doesn't matter if it's positive or negative infinity. So any of these, infinity over infinity or negative infinity over negative infinity, we kind of summarize these to just say plus or minus infinity over plus or minus infinity. The book will actually just write this as infinity over infinity, and it could be positive or negative. Okay, all of those are indeterminate forms. Let me give you some examples of forms that are not indeterminate. Okay, 0 over 1. What is that? If I have a function and the top goes to 0 and the bottom goes to 1, what is the limit? That is 0. Okay, there's no ambiguity there. It's very clearly 0. Let's do another one. Infinity over 1. Top is infinite and the bottom's 1. That's going to go to infinity. No questions there. If I had 1 over infinity, I have 1 over a really, really, really big number that's getting bigger, bigger, bigger. When I take 1 over a huge number, that's really small. So that actually goes to 0. Okay, so these are not indeterminate forms. These are indeterminate forms. Okay? And these forms in particular, 0 over 0 or infinity over infinity, which actually means any of these are the ones that L'Hopital's rule applies to. L'Hopital's rule applies to those indeterminate forms. It does not apply to determinate forms. So do not use this rule that I'm about to show you on things that are like 0 over 1 or 3 over 5. No, don't do that. Okay. There are some other indeterminate forms. Let me go ahead and give you a few other examples of indeterminate forms here. So these are division ones. There are multiplication indeterminate forms too. The most famous one is 0 times infinity. What this means is we're looking at a limit of the product of two things where one of them is getting super small, it's going to 0, and the other one's getting super big, it's going to infinity. So let me give you an example here. Limit as x goes to 0 from the right of x times 1 over x. Okay. This first term is going to 0. The second term, 1 over x, when x goes to 0, the bottom is this is becoming infinite. And it's positive, so it's becoming positive infinity. So this is going to 0, and this is going to infinity. But you can see that if I actually do the cancellation, that cancel the x's, this limit is actually going to be 1. Now I could change this by putting a 5 on top here. The first thing would still go to 0, and the second thing would still go to infinity, but the limit would be 5, not 1. So just because the first term goes to 0 and the second term goes to infinity doesn't mean you know what the final answer is going to be. 0 times infinity is not 1. It's indeterminate. You can't tell. Okay, does that make sense? So contrast that with if I had a limit where the first term went to 0 and the second term went to 0, what would that limit be? Clearly that limit would be 0. Or if the first term went to 1 and the second term went to infinity, that's going to go to infinity, right? Okay, are you seeing what I mean by indeterminate forms versus determinate forms? These things, if I know where the first thing's going and I know where the second thing's going, I'm done. I don't have to do any more work. Here I have to do more work because it's not clear up front. Okay? There's also a subtraction indeterminate form, and then I wrote substitution. So subtraction indeterminate form is infinity minus infinity. If I have something huge minus something huge, we can't tell what's going on. So let me give you an example there. Limit as x goes to infinity, this is kind of a silly example, x minus x. Well, this is infinite and this is infinite. If I actually simplify this, though, the limit is 0. Okay. However, if I went like this, limit as x goes to infinity of x plus 2 minus x. Okay, this thing, x plus 2, is going to infinity, and the other thing is going to infinity, but the overall limit ends up being 2. Okay, so can you see how you can't just tell? Because infinity minus infinity, I don't know. It could be any number of different numbers at the end. But, for instance, if I had a difference of two things, f minus g, and the first thing went to infinity and the second thing went to 0, then clearly this would go to infinity. Or if I had infinity minus 1, that's going to be infinity. Or 0 minus infinity is going to be negative infinity, right? Does that make sense? Okay. And then the last kind of indeterminate form has to do with powers. Okay, there are 3 indeterminate forms related to powers. I'm not going to go through a bunch of examples of why these work, but the 3 are 0 to the 0, 1 to the infinity, and infinity to the 0. Let me explain a little bit why these are indeterminate forms. Typically, 0 to any power is 0, but anything to the 0 is 1. So when you have both of those things happening, they're in conflict with one another, and they want to try to take the limit to different places. That's why it's indeterminate. Same thing here. Infinity to any power any positive power should be infinity, anything to the 0 is 1. So these two are, again, are not agreeing, and that conflict is what causes these things to be indeterminate. 1 to any power is 1, but any number slightly bigger than 1 to the infinity is going to be infinite. So again, these two things do not agree with one another. So these are all our examples of indeterminate forms. The ones that L'Hopital's rule directly applies to are these two. So we're going to look at these today. And then on Thursday, we're going to look at these other examples of indeterminate forms where L'Hopital's rule applies. Okay? L'Hopital's rule will not be on the exam. So just kind of keep that in mind. All right? So let's actually see the rule now. We've gotten a lot of prelude to the rule. Let's actually see the rule. And then we'll do a bunch of examples of the rule. I think you'll like this rule. This is actually a really cool rule. Okay. All right, so the rule says that if I have two functions, f and g, that are differentiable, so we have to be able to take derivatives, and if the limit as x goes to a of f over g, so we're going to be looking at a limit of f over g, if this has the indeterminate form zero over zero or infinity over infinity, and again, when I write infinity over infinity, and plus or minuses are fine in there. Okay, so if the top and bottom are both going to 0, or the top and bottom are infinite, and if the derivative of the bottom does not equal 0 near x equals a, so where we're going to take the limit, except possibly at a, then, and I'll explain what I mean by that, then to do this limit, so I'm trying to do the limit as x goes to a of f of x over g of x, and I'm getting 0 over 0 or infinity over infinity. What you do is you set that limit aside and instead look at the limit of the derivative of the top over the derivative of the bottom. Okay? So we're going to look at a completely different limit. Instead of looking at the limit of f over g, we're going to look at the derivative of f over the derivative of g. And when we do this, we're using L'Hopital's rule, and I like to have a little symbol above the equation to tell somebody I'm using L'Hopital's rule. I do a little L''H right there. Okay, so you'll see that when we do these problems today, you'll see me integrate that into the types of problems that we're doing, okay? All right, now most of the time, you can see why we need this condition of differentiability because we're trying to take derivatives, so the functions need to be differentiable. This condition, most of the time you don't have to worry about it because what it's saying is we just need to be able to have this function in the denominator when we're taking the limit. And if the function's 0 in the denominator completely, that's a problem when we're dividing. This is usually not an issue, and this is usually not an issue. So the thing you need to look for when you're seeking to apply L'Hopital's rule is, are you looking at 0 over 0 or infinity over infinity? So let's do a few examples first. Like what we did previously, way at the beginning of the year, using those other techniques, we'll do normal technique and then we'll do L'Hopital's rule, and you can compare the two. Okay? So let's start with the limit as x goes to 3 of x squared minus 9 over x minus 3. Okay? This type of problem should look really familiar. And how did we do this previously? What will we do? Previously, what we would do is we would factor and cancel. This is one of our factor and cancel problems. So we take a limit as x goes to 3, and we factor the top, x minus 3 times x plus 3. Okay? So we have to make sure we factor right. And then the x minus 3's cancel. And then we let x go to 3. And when we plug in x equals 3, these are both 1 now. So I get 3 plus 3. In other words, I get 6. Okay? That was how we would do that problem previously. Here's what L'Hopital's rule says. Let's try L'Hopital's rule here. Okay? We try plugging in, like we do up here. The thing that tells us to do this is when we plug in, the top is 9 minus 9. In other words, the top goes to 0 and the bottom goes to 0. When you do these problems in L'Hopital's rule, please write this because it tells me that you checked it. It's important that you check it because you will end up getting some problems where somebody tries to trick you and the top goes to 0 and the bottom goes to 1, so you're not actually supposed to do L'Hopital's rule. You're just supposed to do something else. Like if the top goes to 0 and the bottom goes to 1, the limit would be 0 and you'd be done. So you don't need to keep doing L'Hopital's rule. Okay. So what I'm going to do is I'm going to write a little L apostrophe H because I'm about to use L'Hopital's rule. And what L'Hopital's rule says is, instead of taking the limit of f over g, what I'm going to do is take the derivative of the top. So let's take the derivative of the top. The derivative of the top is 2x minus the derivative of 9 is 0. So the derivative of the top is just 2x, and the derivative of the bottom is 1. So L'Hopital's rule says instead of taking this limit, let's take this limit instead. Derivative of the top over the derivative of the bottom. And that limit turns out to be 2 times 3 is 6. And it's a whole lot easier. Right? Okay. Let's try another example here. All right. Sorry, I don't have a very big board here to work with. Okay, let's try the limit as x goes to infinity of 4x plus 1 over 3 plus 5x. Okay. If we let x go to infinity, the top would go to infinity and the bottom would go to infinity. And from what we described previously when we were reviewing these limits, what I should do is I should divide the top and bottom by the highest power of x on the bottom. Now the highest power of x on the bottom is just x to the 1, so I'm going to divide by x and divide by x. And we're going to let, when x goes to infinity, I've got 4x over x is just 4, plus 1 over x. Then the bottom I get 3 over x plus 5x over x is 5. And now when x goes to infinity, this part goes to 0 and this part goes to 0. So I get 4 plus 0 over 0 plus 5, and that gives me 4/5. Okay? That was our old technique. Let's instead use L'Hopital's rule. Okay, so when we do it this time, the top is going to infinity and the bottom is going to infinity. And again, I want you to check that and I want you to show me that you checked it. And then I'm going to use L'Hopital's rule, so make sure that you write that little L apostrophe H, because if you don't write it, sometimes what people write next, it's not clear how they got it from here. Okay, so what we're going to do, L'Hopital's rule says, just take the derivative of the top. What is the top? It's 4x plus 1. So the derivative of the top is just 4. And then divide by the derivative of the bottom is just 5. So we're done. Same answer. Nice, huh? Okay. Now let's look at an example of a problem that we couldn't do previously. So e to the 3x minus 1 over x. There actually is a way that we could have done this previously, but I'm not going to get into that. It's very complicated. Okay. Notice that when x goes to 0, e to the 0 is 1. 1 minus 1 is 0. And the bottom goes to 0. This is the perfect setup for L'Hopital's rule. So what I'm going to do is L'Hopital's rule says take the derivative of the top. So the derivative of e to the 3x, we've done this enough. This is 3e to the 3x, right? You have to use the chain rule, but you've done e to the 3x or e to the something x enough that you should feel comfortable with this. The derivative of e to the 3x is 3e to the 3x. Minus the derivative of 1 is just 0. And the derivative of the bottom is just 1. Derivative of x is 1. So now when x goes to 0, I've got 3 times e to the 0 is 1 over 1, so that limit is just 3. And this was not even a problem that we could do previously. So this is a really nice rule. Okay? All right. Make sense? Okay, there's 2 more examples I want to show you, and then there's a common misperception that ends up coming as you start to see this rule a few times. Okay, let's do limit as x goes to 1 of x minus 1 over x squared plus x. Okay. So the danger once you do L'Hopital's rule a few times is you just kind of get into that L'Hopital's rule crank. And you say, okay, well, the derivative of the top is, well, the derivative of the top is 1, and the derivative of the bottom is 2x plus 1. And so when x goes to 1, the top is 1 and the bottom is 3. So the answer is 1/3. I did something wrong here. Did anybody catch it? I did something wrong. Talk to the person next to you and try to figure out, what did I do wrong? I did something wrong here. What did I do wrong? Okay. Whenever you do L'Hopital's rule, you must check what are the top and bottom doing. The top here is going to 0, but where is the bottom here going? The bottom is going to 2. So when I have a fraction where the top is going to 0 and the bottom is going to 2, what is the limit? It's not 1/3. You cannot apply L'Hopital's rule here. This is bad. Okay, if the limit of the top is 0 and the limit of the bottom is 2, then the limit is 0, right? 0 over 2 is 0. That should be my answer. So please make sure, and I will do this to you at some point, please make sure you don't just get L'Hopital rule happy and start doing L'Hopital's rule where you shouldn't be doing L'Hopital's rule. Okay. All right, let's do another example. Oops, that's not the marker I wanted. Okay, limit as x goes to 0 of sine x over x. Now, I don't know if you remember how we did have a way that we originally did this problem because we needed this derivative for the derivative of sine. But we had to do a bunch of weird trig. We actually had to use the squeeze theorem by drawing a triangle and then having some other circles in it, and then we had to develop the squeeze theorem. This was actually a very hard limit for us to do. Now, I want you to notice the sine of 0 is 0, so the top's going to 0 and the bottom's going to 0. We are set up for L'Hopital's rule, so if I do L'Hopital's rule, derivative of the top, the derivative of the sine is cosine, and the derivative of the bottom is 1, and the cosine of 0, that limit is 1 over 1, which is 1. Nice. Okay, now I'm being a little deceptive here because in order to figure out the derivative of sine, we needed to find this limit because we were doing stuff with h's before. Do you remember that? And now I'm using the derivative to figure out this limit. So you kind of can't do both of those things. I couldn't use L'Hopital's rule in the case when we didn't know the derivative of sine originally, because I need to use the derivative of sine here. But we do know the derivative of sine now, so that makes this problem super easy. All right. Let's do one more. Limit as x goes to 0 of arctangent of x over x. Okay, so because the tangent of 0 is 0, the arctangent of 0 is also 0. So when x goes to 0, the top is going to 0, and the bottom is going to 0. So if I apply L'Hopital's rule, what should be sitting on the top and what should be sitting on the bottom? Let me just let you fill in what's there right now. So take a minute and fill in what should be on the top and what should be on the bottom when I do L'Hopital's rule. Okay, compare with the person next to you, what they have. All right. So what you should see the derivative of arctangent on the top. Derivative of arctan is 1 over 1 plus x squared, right? No square roots, no 1 minus x squared. Don't do that. Derivative of the bottom, the derivative of x is 1. So now when we let x go to 0, the top just goes to 1 and the bottom goes to 1, so this limit is overall 1. Okay. Okay. One common point of confusion that many times comes up here. Students, after they do this for a while, they start asking, well, is this a substitution for the quotient rule? Okay, so I don't know if maybe that occurred to you or not. If it did, you're not alone, and that's a very reasonable question. Okay, so let me write down the quotient rule for a second. So the quotient rule says that the derivative of f over g is low d high minus high d low square the bottom, and there you go, right? That's the quotient rule. L'Hopital's rule says if you're finding the limit of f over g, and they both go to 0, for instance, then L'Hopital's rule would say take the derivative of the top over the derivative of the bottom. Okay. The difference here is that in the left side, I'm trying to take the derivative of this fraction, and on the right side, I'm trying to take the limit of this fraction. Okay, they're close, but not the same thing. And the derivative is a limit, but it's not the limit of the function, it's the limit of a much more complicated thing, okay? So you use the quotient rule when you're taking the derivative of a fraction. You use L'Hopital's rule when you're taking the limit. Okay, this is the derivative and this is the limit of that fraction. Okay, is that clear? So don't confuse those two. I think sometimes people start confusing those two and then they'll try to do the quotient rule on one of these fractions, and that's not the point here. We're not taking the derivative, we're taking the limit and we're using derivatives to find that limit. Okay. Okay, one other note that I need to make about L'Hopital's rule is that you may need to do L'Hopital's rule multiple times. So just like we had with integration by parts, I know integration by parts is your favorite integration technique, right? Just like we might have to do integration by parts multiple times, you sometimes have to do L'Hopital's rule multiple times. So let's take an example here. So limit as x goes to infinity of x squared over e to the x. Okay, so when x goes to infinity, x squared goes to infinity, e to the x goes to infinity. Okay, so I'm going to apply L'Hopital's rule. So I have a limit as x goes to infinity. Derivative of x squared is 2x. E to the x is my favorite function. The derivative of e to the x is e to the x. So now when x goes to infinity, the top goes to infinity and the bottom goes to infinity. But notice that the fraction's actually gotten better because instead of x squared I have a 2x. This is simpler. Okay? So what I'm going to do is I'm going to apply L'Hopital's rule again, which means the derivative of 2x is 2, and the derivative of e to the x is just e to the x. And now the top is going to 2, and the bottom is going to infinity. So I have a fraction where the top is 2, and the bottom is huge. 2 over a huge number is a really small number. This fraction is going to 0. So there I had to apply L'Hopital's rule twice in order to get to a final answer. All right. Let's look at one more example here. Okay, limit as x goes to 0 of sine x minus x over x cubed. All right. So when x goes to 0, sine of 0 is 0 minus 0. The top is going to 0. Bottom's going to 0. So if I apply L'Hopital's rule, limit as x goes to 0, derivative of sine is cosine minus 1, and then the derivative of the bottom is 3x squared. Now when x goes to 0, cosine of 0 is 1, 1 minus 1 is 0, the top's still going to 0, and the bottom is going to 0. So I'm going to do L'Hopital's rule again, and the derivative of cosine is negative sine. Make sure you've got that negative in there. Derivative of negative 1 is just 0, so that top is just negative sine, and the bottom becomes, the derivative of 3x squared is 6x. Now, when x goes to 0, again the top is going to 0 and the bottom is going to 0, but notice the bottom is getting better. The next one is actually the one where I'm going to stop, right? Because the derivative of sine is cosine, the derivative of 6x is 6. The second that this is not 0, I know I'm done. Okay, so now when x goes to 0, the top goes to negative 1 and the bottom goes to 6. And so this overall limit is negative 1/6. Okay. All right, so that gives you an introduction to L'Hopital's rule. And again, L'Hopital's rule applies to any of these indeterminate forms that are 0 over 0 or infinity over infinity. What we're going to do, again, on Wednesday, we've got our exam. If you've got some extra time here, you're welcome to work on some more review problems. And then on Thursday, we're going to look at those other indeterminate forms, the multiplication indeterminate forms, the subtraction indeterminate forms, and then if we have time, the power indeterminate forms there, okay? But I want you to make sure that you get this, the general L'Hopital's rule, down under your belt first, all right? All right. Good luck studying. I'm praying for you guys. Have a great test on Wednesday, and I will see you guys on Thursday.